Um, Generally, an Atwood machine is characterized by just one of two things. It's going to have a pulley and two blocks. That's technically an Atwood machine. Now you can have more, but that's where it starts. So the first ones that you tend to see start with a single pulley, that's suspended by something from the ceiling or something like that. And then there's going to be there'll be a box on either side. So let's start with that. So this is your basic Atwood machine. It's important to understand that there's several things about the Atwood machine that they're going to ask, if they're going to ask about it at all. But there's a couple of straightforward features that you should be able to do right from the start that are things that are about the Atwood machine. Generally, these are almost always going to be either Newton's law problems or conservation of energy problems. Okay? They are not going to be momentum problems. And generally, it really depends what they're looking to do, but there are two or more levels of these problems. If you want to look at it from level of difficulty standpoint, they could have a massless pulley. That is the lowest level of difficulty. Or if they really want to pick it up, then they could make the pulley have inertia. So they give the pulley a mass 2 and tell you it's a disc or a ring or something like that, and you have to deal with the pulley's inertia. So Atwood machine problems are characterized, though, by generally them asking about the acceleration and or the tension in the string. That's very likely the style of problem that they're going to ask. So let's run through the basic method for solving one of these, and then we'll look at a couple of variations, okay? So the basic method or the basic topic typically is a Newton's law question where they want the acceleration of the system or the tension in the string. That is the most basic method. So, like any Newton's law problem, the very first thing you should probably do before you get started is identify a direction of motion that you're going to call positive. I would encourage you to direct that based on where you think the system is going to accelerate. Like if you know that mass 1 is heavier than mass 2, and you know that it's very likely that mass 1 is going to go downwards, then make that your direction that you call positive. Now, it's been a long time since we've had these conversations like this, but if you read the textbook does this different. And they set this whole thing up differently. But I like this kind of consistency. I think it allows for less ambiguity and a more structured approach to solving it. If when you find the acceleration it works out to be negative, you know then that it actually moves in the opposite direction of what you chose to be positive. So we start here, and then the first thing we do afterwards is we make a free body diagram for each of the objects that's in the system. Now, we saw that was one of the things that you were asked to do on the FRQ style questions. And let's be real clear about this. And I'd be, if the pulley has no mass, the tension is the same on both sides of the pulley. That's important. That's a very important detail. If the pulley has no mass, the tension is the same. They tested that on both of the FRQs that we had that were like this. They wanted to see that you drew the tension to be the same size arrow on both of your objects. And further, they wanted you to articulate that the one that is heavier will have a larger weight downwards than the tension is upwards. Right? They want you to be able to show that it's an unbalanced force that causes it to move, so you have to make the downwards weight longer than the tension. That way it's unbalanced downwards. By extension, you have to do the opposite of that on the lighter one. You have to make a weight that is less than the tension. It's not enough to make the weight downwards on both of them uneven. You have to make them uneven and relative to the tension. It's the only way you're going to be able to get the points on that. Now look, they've already asked this question. So are they going to ask this question on the exam again? Probably not. Not this early. They're probably going to change it. That doesn't mean there won't be an Atwood machine. I wouldn't expect this strict problem to be on the exam right away. Now, the rest of this problem is about algebra. You have to apply, Newton's second law, and the application of Newton's second law is pretty straightforward. It's going to be net force equals M2A on that block, and net force equals M1A on that block. Look, they are very likely to give you points just for recognizing that it's an unbalanced force that causes an acceleration. Let's try and get those points. So even if you don't know where to go from here, you write down Newton's second law. It gives you that point. It gives you a starting place, a place for you to be able to get these points. After this, you shouldn't eat greens. They're bad for you. That mold will get to you. So make sure that when you've decided what direction is positive, that you follow through with it when you're doing your net force discussion. Make sure that if it points down and you said down is positive, you make it positive. So many exams I grade from you guys, it's little things like that. It's all these little tiny details. And I know there's a ton of these little tiny details. It's still up to us to try and do our best to try and work through them. So the next one, we're going to have tension minus M2G equals M2A.
All right. Are you guys the EP study group?
Yeah.
We have people going up to the services thinking Target's putting it on, so we'll just send them over this way if...
Okay, Target. Sorry, I didn't know the Target wasn't putting it on.
No, you're fine. Just there was some confusion where...
Okay.
So we'll send them over this way.
Thank you. You guys do understand that Target had nothing to do with this, right?
Yeah.
Now, at this point, all we have is algebra. You guys understand that, right? This is an algebra problem from here on out. So they're only going to give a point for something like this, and they're not. This exam has not been largely about the mathematics. It's, as you've noticed, it's going to be about other things. So you should be able to deduce other things about this that aren't about the mathematics. For example, just from looking at what we've drawn here, it should be reasonable for you to figure out something like the tension up here is not equal to the weight of the two boxes. That, it's a weird statement, it's what a lot of people don't realize, but that's a great question for them to ask. A lot of people think that because the two boxes are being supported by the pulley, that the pulley will be pulling downwards with the weight of both of these. And that would be something everybody would jump to as being the right answer, but that's not true. The boxes are moving, they're accelerating. The center of mass of this system is actually moving downwards, so the tension upwards is always going to be less than the weight of the two boxes. And that's because the system is accelerating. Because it's accelerating, it doesn't support as much of the weight. In fact, the faster it accelerates, the less of the weight is being supported by the pulley. So it's little things like that that are the questions they're probably more likely to ask, because it's not going to be a strictly mathematical test. So although we should be nervous about the math a little bit, getting to this point is probably 5 of the points of a 7-point FRQ, with 1 point being for just manipulating the numbers here. So as we saw on the one that was like this, they gave 1 point for your free body diagram being correct, but another point was for the tensions being the same. 2 points just for that. You're left with 5 points left to try and get the rest of the problem. And so setting up the Newton's law part, that's going to be a part 2. All right, so how many of you need me to finish this? Are we good?
Quick question. So if the mass, so if it's accelerating and the center of mass is going upwards, would the tension be greater?
It can't be the center of mass going upwards. Gravity wouldn't do that.
Gravity would pull the center of mass down.
Right.
Okay.
Got it.
So since we've done this one already, let's change this to be probably the next kind of problem that you might see on the exam, which does change this enough to be worth going through. And that's if the pulley itself has mass. Because that's a big difference, and that changes so much of what happens here. Now, let's for the time being say the pulley is a disk, it has a moment of inertia of 1/2 m3 r squared. Okay, so I'm going to make it a disk. I'm going to say its mass is m3. This would be the right year for them to ask this question because it's never been asked on an FRQ yet. So having the pulley have inertia, this is a possibility. Remember last year they had that wheel rolling down the ramp as one of the questions, and that's where they asked about rotational inertia. So seeing this one be a rotational inertia problem to me is very likely. Now, of course, that means it's not on the exam because I just said that, but there are some critical differences here. And this is the most important. This is the one that you should emphasize. The tensions aren't the same on both sides of the pulley. The tensions are not the same acting on the two boxes. That's the takeaway. It means that and this comes right back to Newton's laws. There are two tensions for sure. But remember, the only way the pulley can actually rotate is if there's an unbalanced tension acting on it, which means the two tensions have to be different. So the moment they say that your pulley has inertia, the tensions no longer are the same. It's like some of the tension is used up as it goes across the pulley so that there's an unbalanced set of tensions on the pulley. So the left side, I would call that T1, and the right side, I'd call that T2. The two tensions will have to be unbalanced. Now, this part's also important to recognize. If you know which side has the heavier box, that's going to be the side with more tension, because that's the direction the system will accelerate. So, when you start drawing your free body diagram, T1 on box 1 won't be as big as T2 on box 2. You should draw them separately with separate sizes. This makes sure that we have an unbalanced torque acting on the pulley. And then there's still the weight of box 2. There's still the weight of box 1. And now you have an even bigger problem to deal with. You have the fact that there are two tensions acting on the pulley. One is acting to cause it to turn counterclockwise, and one is acting to cause it to turn clockwise. But there are two torques acting on the pulley. So let's take a look at the forces on the boxes first, because those are easy, and then we'll look at the torques on the pulley next, because that's not so easy. So everything about the boxes largely remains the same. The net force on box 2 is going to be equal to M2A. There are two forces acting on it. There's tension upwards and weight downwards, and that equals MA. Hey, Parker.
Hi, how are you?
All right, back to work. Net force equal, and I feel like this is largely very repetitive because we've already done this, but why not be repetitive? I have nothing better to do. There it goes. So we saw all this, right? This is all the same. The biggest problem now is we can't actually put these two things together like we did before. Before, the tension was the same on both, so we could solve for one and plug it into the other. That made it pretty easy. But these two tensions are different, so they can no longer simply be connected together. That's what makes this really hard. And that's why I don't think they will ask the mathematics of this, because we now have to deal with the torque on the pulley. And a torque on a pulley adds the last piece of information that will let us work this out. But torque is, a whole different animal, and you guys know that. So let's talk about the torque for a minute. I'll remind you that it's Newton's second law, but it's just for torques, that the net torque has to equal I alpha.
Couldn't you combine the two sides together through the acceleration? Because don't they share the same acceleration?
Yeah, you could, but I would still give you a one relationship with two unknowns, T1 and T2.
Yeah.
So it won't give us we won't be able to figure out the acceleration from that. Because right now, the truth is we have three unknowns. A, T2, and T1 are the three unknowns in the problem. Likely. I mean, they could give us A and then we don't know the mass. Something's gonna be unknown. That's why it's a stupid physics problem. But it's still gonna be this, ultimately, guys, it really comes down to the fact that this is still the unbalanced force, which is the tensions, is equal to the acceleration of the system times its inertia. That's still going to be in there. I'm pretty sure that what we're going to see in the answer is the entire inertia of the system now, which is going to have to include the pulley. That's really what it comes down to. I bet at the very end it'll still be M2 minus M1. That's still got to be the answer, because that's still the unbalanced force acting on the system. But now we have to work in the inertia of the pulley, which is likely to slow the system down. Now, so I mean, if you really want the simplest takeaway, to be able to get points without doing the math, and this is something I would emphasize for all of you, is remember, this is not supposed to be a heavy math class, even though they ask some heavy math on the exam. You should be able to say whether the system is going to accelerate faster or slower with the pulley having inertia. You should be able to say it without having to go through all of this. I mean, what does the pulley's inertia do to the system? Does it make it easier to turn or harder to turn?
Harder.
So I think you guys could probably, just with that knowledge, recognize that the acceleration is going to be less, since you now need work to turn that pulley. So be flexible in your ideas here, that you don't have to prove this mathematically. That if there's a checkbox that says, okay, the pulley now has inertia, does it accelerate faster, slower, or the same? Don't jump to the same. Think it through. Has the inertia of the system changed? If it has, how's that going to affect your answer? If the inertia increases, it's going to accelerate less. That is appropriate justification. That one sentence. So, be prepared to do that. Not have to prove it mathematically. That's my go-to thing all the time, and it shouldn't be. Now, I'll be honest, I think I know what the answer is going to look like. I think, and this is without having solved it, I think it's going to be M2 minus M1G on one side. And I think on the other side, it's going to be the inertia of the system, M1 plus M2 plus something with M3 in it, times A. I think that's what it's going to look like. And I bet it's going to be a 1/2 out in front of that M3, because there's a 1/2 in front of the moment of inertia. That's my guess as to what the answer will look like. I'm bringing it up because on a multiple choice, look for that. You look for that one there, because
Is that M2?
it's supposed to be an M3.
Okay.
It's an M3-ish, maybe.
What's it being multiplied by?
That's
A.
That's got to be an A. I just ran out of space, dudes. I'm trying. Dudes. All right, so let's try it out. You guys want us? We can do it. It's not gonna be that hard to do. It's just all that math. So let's remember a couple things that I think you guys have difficulty with. First, this side right here, where I have I alpha, you're gonna have to put in the moment of inertia, and you're gonna substitute A over R for alpha. You can't see that at all.
Wait,
Can you see it better now?
A over R for alpha?
A over R for alpha. Yep, because look, the whole thing is going to have the same acceleration, but the pulley doesn't actually go anywhere, it rotates, but its rotational acceleration is still related to the outer edge's linear acceleration. So you're always replacing, in these kinds of problems where you have something that's moving in a linear fashion and something that's moving in an angular fashion, you are always replacing the angular velocity or acceleration with the linear velocity. And for whatever reason, it magically cancels out. You guys going into C, we figure out why it cancels out pretty fast, but the radius never seems to matter. All right, so let's finish this up. The left side, That's where I have the net torque part. I have to actually find the torque, and this is where these problems kind of stink, is that torque is not force. Torque has all of that, right? It's going to be the radius times the force times the angle. But for a pulley, the angle is always 90 degrees, always. So for a pulley, the sign never matters. If you try and change the angle, it just peels off at a tangent anyways. So pulleys always have a sign of 90 degrees in their answer. R is going to be the radius of the pulley. That leaves us with the force. I think the hardest part about these is recognizing for yourself what direction is each of the torques. Right now, we've stated that counterclockwise is positive. So, this tension is causing the counterclockwise torque. So that's going to be RT1, and it's positive, minus RT2, because it's clockwise. That makes this the torque equation. It's got two torques in it, T1 and T2, and it's got all the other radius stuff in it. God, it's a mess. This whole page is a mess. This class is not a mess. All right, so keep going. Are you sure? This is like hard.
Yeah. Go.
I do think this is harder than what's going to be on the exam.
Okay, so this isn't going to be on the
I don't think they're going to do this on the exam. I think this is too much math. I think that,
Just keep going.
What?
like,
Well, if it's not going to be on the
I don't think it's going to be on the exam. But I do want you to know, I think if they do this on the exam, they're going to have the pulley be massless, and then they might ask you qualitatively what happens when there's mass to the pulley. I think that's what they'll do. This kind of problem, this takes it outside the tenor of the course. I think there's just too much math here. Now, just point of fact though, if you look at what's going on here, all the R's cancel out. You might not see that, but you've got an R in the denominator here, and then you have an R on this side here and here. They're all going to cancel out, and this actually becomes just T1 minus T2 equals 1/2 M3A. Now, just so you know, you guys probably can't see enough into the future, but look at what T2 has in it. T2's got M2G and M2A. And look at T1, it's going to have M1G and M1A. So when you put all of it together, you're going to get exactly what I said. The weight of the left box minus the weight of the right box equals the inertia of the system. That's what we said was going to happen. Now, let's take a look at one more Atwood machine question, because this has been on every exam that AP has given. So it's worth looking at. It's shown up either on the multiple choice or in the FRQs. There's been an FRQ on it once, and it's been on one of the practice tests. Just so you guys know, the practice tests, or what they call the practice tests, are the international versions of the exam. So anybody who takes the makeup exam gets that. Also, I've gotten an email telling me that they're giving two versions of the exam during the exam time. I got that email on Friday. They did last year too. There were two different exams out there, so just be aware, half of you are getting one exam and half of you are getting a different one. It is quite possible one of you guys will have a harder exam than the other. They assure us though that you guys are not compared together. Do you guys understand that?
So the group with one scale.
The group that has one exam is compared together with themselves, and the group that has the other exam are compared together. So they assure us that that's the way it's fair. Just so you know, though, they do it in all the exams. It's likely you've had a different exam before in human or in world. So.
don't even remember world.
I hated that world BBQ.
I don't remember. It was literally 6 pages.
All right, so
It was awful.
the AP World exam.
Yeah.
It wasn't that bad.
No,
Alright,
that's terrible.
There's always one person who says stuff like that just to piss everybody off.
5.
You got a 5 on world?
A 5?
Good job, buddy.
Wait, what?
That's awesome.
I got a 3.
I got a 3. I was happy with that.
Yeah,
I was. I thought I was gonna get a 2.
Yeah.
Good job, Prom. All right. Don't let anybody take this away from you. Of course, you have to pause a whole lot here. That's different. In fact, I'd argue that this is easier than the other one because only one force actually acts to move the system, and that is the box that is hanging off the table. That one's the one that's causing the system to move. The rest of the system responds to it. So an Atwood machine question like this uses this box as the lone force acting on the system, but this box and this box together represent the inertia of the system. So this sounds really, really bad, but you could use all that net force stuff to figure this problem out, find the torques and the tensions and all that. But let's just consider what this actually says and realize that we can probably figure out this problem in one step without having to do any work. All the forces acting on the system equals the inertia of the system times the acceleration. The only force that acts on this system that matters is the box off the table. That's the only box that matters. That has to equal the inertia of the system. That's the inertia of the system times the acceleration. And you guys realize that's all there is there. Newton's second law is about the unbalanced force causing your system to accelerate. I didn't draw one free body diagram. I didn't do any of the other plugging in or substitution. That is what the system is about. We tend to get, and I am the first one to be at fault for this. We tend to get bogged down in the details of there's tension and free body diagram, but Newton's second law can be used globally for any system like this. If you know what's causing your system to move, that's the unbalanced force. If you know what the system's inertia is, put it in for the mass. That's what's happening to your system. Now, we can go the long route. There's a single tension to the right that acts on box 1. It's the only force that matters on box 1, so tension equals M1A. That has to be true. Yes, I know box 1 also has weight and normal force. Does that part really matter if there's no friction? There's no friction, it doesn't matter. It's not causing the box to move. The one that's hanging off the table is experiencing two forces. It has weight downwards and tension upwards. The weight downwards got to be greater than the tension. Net force on box 2 has to equal M2A. So we'll get M2G minus tension equals M2A. You guys see that there's a substitution here, right? You guys all see it? So all of a sudden you've got M2G minus M1A equals M2A. And before you know it, you have exactly what we said before. It has to work out this way. It has to. It has to be the unbalanced force equals the inertia times the acceleration. So, the obvious next question. What happens if the pulley has inertia here? Does it speed up the system or slow it down? What do you think? Yeah, does it? If the pulley has inertia, it makes the system harder to move. It's going to make this side bigger. It's not going to add any force to the system, but it's certainly going to make that side bigger. Could we put in a value? Sure, we could put it in. We could go through the whole route we just did in the last question, but all of you realize that's just making it more complicated. They're probably not going to do it more mathematically complicated. They're going to simply ask, how does adding inertia to the system change the system?
There's only two boxes represent the inertia.
What's that?
I thought you said the two boxes represent the inertia.
The mass of the two boxes represents the inertia. If the pulley suddenly has inertia, then I don't want to say just its mass, because it's the distribution of the mass that matters, but its inertia, its moment of inertia will somehow have to be included. I do want to tell you though, if they add a pulley with inertia, you do have to remember that the two tensions are suddenly different. They won't be the same. This will be tension 2, this will be tension 1, and they will not be the same tension because now we need an unbalanced tension to cause the pulley to turn. That's it. That's all there is about Atwood machines. They are going to be on the exam. They're going to be in a multiple choice. There's going to be an Atwood machine in multiple choice. We've seen it on every released exam. There's been at least one Atwood machine problem on the multiple choice. Whether or not it's in the FRQs, I think you have a 50% shot of there being some kind of Atwood machine on the FRQs. Because in the last 3 years, 2 of those years have had an Atwood machine on the FRQs. So I think it's not unlikely. I would say it's a 1 in 2 chance.
Say the pulleys still didn't have any mass, but friction was added to the system. Would the tension still be the same, or would they be different now?
It depends on where the tension is. So I don't know if you guys heard Alejandro's question, but it's a great question. What if we had this problem again, but friction is in the system? There are only 2 places that friction can show up in the system. They can show up between block 1 and the surface. Or they could put the friction in the axle of the pulley. Those are 2 places where it could show up. Now, Alejandro asked if the tensions would be different if there was friction. So let's consider each case separately. There's a lot drawn here, so perhaps while somebody's getting ice, I'll take a second to redraw it. And Narav, you're welcome to pull up a chair. There's lots of them. All right, back to the same thing, right? Looks similar? If there's going to be friction here, what direction will the friction be? Right, so if there's friction, the frictional force will be against the tension. I can't even tell you if the system moves unless we know more about the friction. Because the friction could be greater than the tension and it stays in place. Or the friction could be equal to the tension and it stays in place. The friction couldn't be greater than the tension, by the way. But it could certainly be equal to the tension. In which case, it could prevent the system from moving at all. That's highly possible, but that does not affect the tension in the strings at all. Now, it might change the value of the tension, but the tension will be the same on both sides. Because the only way the tension will be different is if it takes an unbalanced torque to cause the pulley to move. So, as long as nothing has changed about the pulley, the tension will be the same everywhere in the string. Now, if instead there's a torque due to friction, that looks ugly. There's a torque due to friction in the pulley. Now, that's a highly possible question. It's a good one, too, if I think about it, because it doesn't have to change very much about the system. You can even have a pulley that's still more or less got no inertia, but they could add friction to the pulley. If they do, then it takes an unbalanced torque for the pulley to move, which means that it would change and give you 2 different tensions here. Because there would have to be an unbalanced torque to overcome the friction in the pulley. So even though the pulley doesn't have maybe any inertia, you're still having to fight against the frictional torque that's in the pulley? So that's a good question, and one that'd be, that's worth at least having a pedestrian view of it. That if there's torque in the pulley, if there's friction in the pulley, it would unbalance the tensions. Do you think it would slow down the system if there was friction in the pulley?
Yes.
Yeah, I think it would go slower. Not because the inertia changed, but because you now have introduced a new force to the system. And that force is acting to prevent motion, which is what friction generally does.
Is it likely they're going to have a pulley that has friction and a pulley that has mass in the same problem?
No, not mathematically. They could ask about that, but that would only be you having to say that there's still an increase in inertia. It wouldn't change anything else. They're separate ideas.